Hello everyone, my name is Joey Tsagay and it's lovely to be here. Today we're going to be talking about security constrained economic dispatch of renewable energy systems. As per my breakdown, we are going to start from why we need security constrained economic dispatch of renewable energy systems in the first place, which means a motivating problem. Then we will move on to the fundamentals of renewable energy systems, followed by the mathematical security constraint economic dispatch problem formulation, objective function formulation, constraint function, identify limits and bounds, then and case studies considered. We will list and discuss about the case studies considered, followed by the simulation results and discussions, and finally we'll be able to try to conclude what we have articulated in the presentation. So let's jump right in. When a sudden interruption or blackout occurs, we notice the importance of electricity in our daily lives, as it everything we do in a day in day out activity in day out activities is based on electrical energy. A sudden and uncontrolled power outage can cause a highly regarded threat to social and economic endeavors of society. For example, let's consider Ethiopian electric power system, a power system of renewable energy sources. The supply power interrupts every time it rains. The supply power interrupts during weekends. Supply power interrupts during holidays. An estimated 85% of customers participated in an interview said that they are sick and tired of the recursive interruptions during holidays, weekends, and when it rains. So these interruptions can impose devastating damage to production plants, service centers, and home appliances. Officially, the blackout report data of Ethiopian electric power system from 2013 to 2016 reported 15 major blackouts. Due to these blackouts, production plants, service centers, industries, and home appliances were down for an average of 4 months. External incidents, equipment failure, and supply-demand mismatch, collectively known as contingencies, cause most of these blackouts. As you can see from the picture, this is a wildfire disrupting a normal power operation. This is kind of contingency, which leads to blackout, which leads to supply-demand mismatch. This is the example. The first challenging aspect of power system operation is that electrical energy, unlike other commodities, cannot be stored in significant amounts. This aspect requires accurate method of balancing generation and demand. Demand and generation should be balanced. And with considering generation limits, transmission security, constraints, contingencies, and uncertainties. This method is called security constraint economic dispatch. And its objective is to minimize operation cost while respecting the operational constraints, and it includes maximizing the system security level. The second challenging aspect is in regard to intermittency and variability of renewable energy sources. With the increased emphasis on renewables to mitigate climate change effects, emerging challenges affect the power industry from advancement. For example, a slight or a small change in a variable renewable can cause a large surplus or large lack of power output that can lead to under frequency or over frequency, subsequently leading to what is called voltage collapse. And this slight change also affects the security and adequacy of power system networks with limited flexibility, such as ours. In order to check whether state of the art is enough or not, we conducted a separate paper on security constrained economic dispatches, and accordingly, a substantial number of articles reported SCED in the perspective of artificial intelligence, renewable energy systems, and post-disturbance corrective actions. So in this study, our focus is only on problem formulation for security-constrained economic dispatch of renewable resources, identifying the challenges posed by penetration of RESs, recommending a hybrid, computationally intelligent method to solve the security-constrained economic dispatch. So what are renewable energy systems, by the way? They harness two or more forms of locally available renewable energy resources to supply a demand in an efficient, cost-effective, and practical way. And their contribution is globally increasing. This is a trend, and we believe this trend will continue. Due to the increasing level of uncertainty introduced by RES, because of their intermittency, their variability, traditional decision making, such as power system planning, power system operation, unit commitment, economic dispatch in the electric power industry are gradually shifting towards stochastic decision making. This is because RES are site specific, they are stochastic in nature, they are unevenly distributed around the world. Though they are modular, they depend on the climatic conditions and geographic factors of the site under consideration. The most often used RES are biomass, hydro, solar, wind, and geothermal. Such systems can operate in both off-grid mode and when connected to centralized grid, with a prime significance of energizing and electrifying remote rural areas, helping to achieve sustainable development goals and improving social welfare or social well-being of the considered community. In this study, RES comprising of biomass, hydro, solar, wind, geothermal, and renewable thermal with their problem or objective formulation and constraint formulation are discussed. Now let's proceed to their mathematical framework. In a practical power system, SCED problem is non-linear and multi-objective due to operational constraints. So multi-objective optimization scheme is selected here, favored with its general form given in the slide. Multi-objective SCED entertains two conflicting objectives. The first one is minimizing generation cost. The second one is maximizing security levels. So we have two weighting and conflicting objectives here. So F1x, as part of the general multi-objective optimization problem, F1x represents objective function of hydropower generation. Hydropower generation depends on the head of the dam constructed. F2 of x represents objective function of wind power generation. Wind power generation depends on the wind speed of the site considered, and as wind speed is stochastic in nature, its characteristics, its behavior should be studied using variable probability distribution function, period the allocation of reserve and penalty cost functions. And F3 of x represents objective function of solar PV generation. Here, solar PV generation depends on solar irradiance or solar radiation. Solar irradiance is also stochastic in nature. So the probability distribution function for the power output of variable or intermittent solar irradiance can also be determined using variable probability distribution function. The fourth one is F4 of x, which represents objective function of thermal generation. Here, for this study, conventional thermal power plants, geothermal power plants, solar thermal power plants, waste energy plants, biomass plants are collectively termed as renewable thermals. So F4 of x represents the objective function of these generating units. Now let's proceed to the constraints. the limits, operational or the design constraints. In a practical power system, continuously respected operation constraints ensure reliable and secure operation. So the constraints considered for this study are demand and generation balance, generation limits, upper and lower bounds, prohibited operating zones, transmission constraints. In our case, Cron's loss function and loss coefficients are considered. Security limits with a credible contingency with the consideration of number of security levels. Generator ramp rate limits. This especially is applied for solar to remove the duck curve challenge. Spinning reserve limits. Spinning reserves are important when a contingency or a blackout happens. They can be used as contingencies. Water discharge and reservoir limits. These are used when hydrothermal systems are considered. Hydrothermal systems like hydropower, geothermal, or solar thermal systems. And the final constraint considered for this study is penetration rate constraint. This shows how much, or in what percentage, in what rate is the power system penetrated by renewables. And in order to check the robustness of the mathematical framework, we have to use case studies or international standards or benchmarks. So the considered case studies are neural 118 test system or 118 bus system, IEEE 118 bus system, modified New England 39 bus system, and part of Ethiopian renewable energy systems. We have selected them because they have high renewable penetration features. Solution method employed is multi-variable, multi-objective optimization method. On MATLAB, we can code it using fmin-max. Tools used are Silent for identifying the effect of multivariable, identifying the effect of penetration rate, and MATLAB for the MVMO. This is the data resources. You can check them out on the internet. Now let's move on to simulation results and discussions. The result of SCED of RES obtained from Silent Power Factory are displayed to show active and reactive power dispatch, voltage and power angle deviation of New England 39 bus system with and without renewable energy system penetration. You can see the differences, the effects, how they are affected, and this shows the effect of RES penetration to a New England 39 bus system. In this slide, the first picture to the left is about generation cost in a hourly and minutely basis, dispatch megawatt with respect to the type of generating units is displayed. And the second one is about generators and their power contribution, in which we call it energy share, which type of resource addresses which dispatch and time it takes to dispatch. You see, to dispatch is to order a generator to generate more or less power based on the demand supply balance. So these results show accordingly. In here the table shows presents the results of selected generating units, which means it presents the power dispatch of committed generating units with their economic cost and power transmission loss. And the total megawatt hour dispatch of RES for neural 108 bus system are also displayed here. This is in a hourly interval. This slide is about some part of Ethiopian renewable energy systems. We have the contribution of generating unit in dispatch value. We have the time with cost generation with respect to cost of generating 1 megawatt of energy, and we have the time over 24-hour time horizon of the dispatch output. So far we have discussed about mathematical formulation of SCED for renewable energy sources comprising of biomass, hydro, solar, renewable thermal, wind, and wind. Constraints, credible contingencies, penetration rates, and limits are incorporated to this formulation. And we have tested the robustness of the mathematical framework on two test case study, two benchmarks, and one physical power system. Modeling and simulation was conducted on MATLAB, MATPower, and Dixilent. So the simulation results show that economic dispatch of RES with their security constraints is a promising step towards the realization of smart and modern grid operations, as it can minimize operation cost, maximize security level, and decrease number of recursive blackouts. You have been delightful audience. Thank you for your attention.